Good morning, everybody. Hold on, my camera is not on. I thought it was. This one? Maybe. It's loading pretty slowly. There it is. All right. Sorry about that. I thought I had it on. All right. So we are on lesson 3, exponential growth and decay. And your homework tonight, instead of being in Delta Math, is actually going to be the first page of the homework attached to this PDF. And feel free to do it on a separate sheet of paper. When your homework is done, you're just going to email me a picture of it so I can check it that way. So let us begin. It says there are many things in the real world that grow faster as they grow larger or decrease slower as they go smaller. These types of phenomenon, loosely speaking, are known as exponential growth and decay in the case of decreasing. So, oops, wrong screen. All right. So here's an example. The number of people who have heard a rumor often grows exponentially. Consider a rumor that starts with 3 people. Sounds important. Starts with 3 people, and where the number of people who have heard it doubles each day that it spreads. So, why does it make sense that the number of people who would have heard the rumor would grow exponentially? So, the more people that know the rumor, so the more people that know the rumor, the faster it will spread, since more people can tell it. It is very similar with the coronavirus that's going on too right now. The reason we're doing this social distancing and staying home is because if we're home, we're not spreading it to other people. So you're really chopping off a lot of other people that could possibly get it. Because say you get it and then you pass it to like me, your teacher. And then I see hundreds of people each day. Now all those people have it. And then those people go home and then they spread to their families and it grows like crazy. Whereas if you stayed home, that whole chain never happened. So very similar to this. So a little real life exponential action happening. And if you look at the curve, it is right now. Mathematically speaking, it's exciting. Not the death part. Not exciting. Not good. Not good. But the math part, very applicable. And as we see it's starting to go down, it might look more parabolic. Anyway, getting ahead of myself. So part B. Fill in the table below for the number of people N that knew the rumor after D days that it spreads. So at day 0, 3 people knew it. Now if that doubles on day 1, that means now 6 people knew it. And then if it doubles the next day, that means 12 people know it. And then if it doubles even another day, 24 people know it. Why is my PDF not writing? What happened? Weird. Oh, there we go. I don't know what the delay was about. All right. So 3 people knew it, then it doubled, so 6, then it doubled 12, then it doubled 24, then it doubled again, 48, then it doubled again, 96. Dear God, after 5 days, 96 people know it. And it could go even bigger from there. What's happening? It's delaying again. There we go. Okay. Not sure why my computer doesn't like me today. It's fine. It's probably thinking, you've never used me so much. How is this happening? So let's try another example. We'd like to determine the number of people who knew the rumor after 20 days. But to do that, we need to develop a formula, N, the people knowing the rumor, if we know D, the number of days that have spread. So if you think about this, a couple units ago, we did sequences where there were recursive formulas and there were explicit formulas. If you recall, the recursive formula was you had to do, like if I want to know the 20th day, that means I need to know days 1 all the way through day 20, whereas an explicit formula, I could just plug in any number and I can find out, you know, that 20th day or the 50th day without knowing, you know, all the ones in between. So that's kind of what we want to do here. So remember, D is the days, and N is the number of people who know the rumor. So if we break this apart, we have our numbers from our tables. Remember, we're doubling. And when you're doubling, that means you're multiplying by 2. So we started with 3, and then we did 3 times 2. Remember, that gave us 6. I'll even put that on there. 6. And then the next one was 3 times 2 times another 2, which was 12. And then the next we had 3 times 2 times 2, which is really like squared, times another 2. That gave us 24. And then since we did another 2, I can do 3 times 2 cubed times 2 to give me 48. And then if I continue this even more, I have 3 times 2 to the 4th power times 2. And that gives me 96. So if I want to analyze that pattern to create a formula, I can say N equals the number of people know. It started with 3, and then it's 2 to whatever number of days that is. So if we look at our pattern there, on the 5th day, there were technically 5 groups of 2 there. There were the 4, and then I had to combine another 2. So remember, when you're multiplying like bases, you add those exponents. So really, those are all like 2 to the 1st. So it's 3 times 2 raised to the number of days that have passed. So if I want to know at 20 days how many people would know the rumor, I would do N, or I can even say like N of 20 if I wanted to write this in function form, equals 3 times 2 to the 20th. And that's going to give me a very large number, 3 million. 3,145,728. Wow, wow, wow. After 20 days, over 3 million people know this rumor. Man, I hope it's not a juicy one. That's a lot of people knowing a rumor. A lot of people. So exponential, as you can see, grows very, 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 very quickly. So next is exponential growth can be very fast, as we just saw. 3 million people. Whoa, that's a lot. Assuming our equation from part B holds, how many days will it take for the number of people knowing the rumor to surpass the population of the United States, which is approximately 315 million people? Well, if at day 20 I'm only at 3 million and I want to be more than 315 million, we got to do a little guess and check here. Excuse me. Eventually, when you get to Algebra 2, you'll be able to solve it, but that's in a couple of years. So let's try, oops. Oh, my pencil's gonna die. Ah! Okay. So let's try like 25 days. Let's just see. If I did 25 days, that would be 3 times 2 to the 25th, which is gonna be 100,663,296. Well, that is too small. That is too small. And if I'm doubling, then I know that 26 days would be like 200 million. So let's try a little bit bigger. Let's say 27th day. So that'd be 3 times 2 to the 27, which is going to be 402,653,184. So yes, this works. So 27 days would be our answer for that. I'm going to have to plug in this Apple Pencil for a minute. Where is the port? All right. So let's just review what we did so far. We looked at a pattern to create our formula, and we saw that it grew rapidly. So this was clearly an example of exponential growth. So I bet the next one might be decay. We shall see. All right. It says now look at the now let's look at developing a fairly simple exponential decay model. Predicted that so good. Helmut from Finland that's an interesting name, is heading towards a lighthouse in a very peculiar way. He starts 160 feet. 160 feet from the lighthouse. On his trip, he walks half the distance to the lighthouse. On his next trip, he walks half of what's left. On each consecutive, he walks half and half and half and half and half and half and half. So, we want to figure out how long would it take him to approach? Would he even approach if he's only going half the distance, half the distance? I mean, he's going to get super close, right? But is he actually going to touch? I don't know. His nose might be really close, but I don't know if he's actually going to touch. So let's see. So he started, so our table shows that he started at 160 feet away. This is where we started. And half of that, the next day would be 80. So then half of that would be 40. And then half of that would be 20. And then half of that would be 10. So it says each entry in the table could be found by multiplying the previous number by what number? This is always important because, this is important because we always want to think about exponential functions in terms of multiplying. Well, if we were dividing by 2, that's really like we are multiplying by a half. Multiplying by a half. So, like in exercise 2a, we want to see if there's a process with repeated multiplication. So, at day 0, at day 0, we were at 160 feet. At day 1, we were at 80 feet. At day 2, so each time we're increasing, we're physically multiplying by another half. So if I was going to write that out, it would look like, oops, my pen froze. 160 times half squared, which would give us 40. And then if I did that again, we'd have to increase it by even another half. So we would have 160 times 1/2 cubed, which would give us 20. And then we would have 160 times 1/2 to the 4th, which would give me 10. So very similar to our last equation. We're going to have d, the distance equals 160 times half raised to however much time has passed. So if we were looking for when n is 5, that would be my exponent again. So E says, how far is Helmut from the windmill after 6 trips? So that would be like d of 6 equals 160 times 1/2 to the 6th, which would be 2.5 feet. So is he there yet? Nope. So let's see. At 10 trips, he thinks he's going to reach it at 10 trips. Let's see if he's right. We'll do d of 10 is 160 times 1/2 to the 10th, which is super close, but technically it's not there yet. 0.15625 feet. My goodness, he's not even a foot away. But it's still no. We need to reach would be 0 feet. So if we actually reached it, we should get a 0. But we got a super tiny decimal, so we're like this close, but we're not actually there yet. So G says, I'll change my color so I don't get smushy here. Explain why Helmut will never reach the windmill. So, since he is going only half the distance, he will get super close, but always have some distance to go. So even if I was half an inch away from it, we would have to go half that distance. You know, so we'd be at 1/4 of an inch and then an 1/8. Like, you know what I'm saying? It's going to get so close, but we're not actually going to touch it. Super, super close. All right, and then one more question. It says, why is the domain for this function always whole numbers? So think about that. What did that domain mean when we were going 0, 1, 2, 3, etc. So the reason is because it was his number of trips. So the domain is measured in number of trips. So you can't take half a trip. You're either going or you're not. You know, it's black and white. So, hope that was okay. Your homework tonight, I just want you to do this front page. So just this front page attached to your notes. If you want to try the back, you can. But I'm only asking you to do this front page. So again, the PDF is in the Files tab. When you're done with it, just send me an email with a picture of your homework. I think you can just take the picture with the camera on your Chromebook. If you have any issues, just let me know. And if you want to Zoom me to check it, that's fine too. It's not due until Tuesday, which will be your next lesson. So I hope you have a fabulous day and have a happy Easter.